Well, hello. As I introduce this video on momentum and impulse, what I want to tell you is that what you're going to see here is probably not a new kind of physics problem to solve, but a new way to solve it. Perhaps we can call it a new language in which to solve these physics problems. And I want to show you where the momentum impulse idea comes from. And it comes from a very familiar idea, which is Newton's second law combined with Newton's third law. So I'll show you kind of how we derive the idea, and then show you an example of when we would probably want to use it instead of Newton's laws to solve a particular problem. So when we usually use this is when we have an object that's moving and we have a force acting on it, and we'd like to know how the object's motion is going to change as a result of that force. So in the past we would have said, well, F net equals ma, that's the Newton's second law idea. And so we would, at least the way I would teach it, is you would draw the object and figure out what all the forces were that were acting on it, and then figure out which ones were responsible for being the net force, or the unbalanced force, that caused the acceleration. And then you call that the net force, and then we'd solve for the acceleration. And then the textbook that we use in my class now, which is Dr. Knight's second edition, then sometimes he'll ask questions like, okay, now how fast is it moving? Well, now what I'm going to show you with the impulse momentum idea, we can go directly there without passing through the acceleration. So let me just rewrite something here. First, I'm going to replace F net with just F, and we'll assume maybe we figured out what that one net force is that's acting on it. All I'm going to do here is rewrite the acceleration as really its definition, which is the change in velocity divided by the change in time. So we're looking over some amount of time. We have some change in velocity. So if we just change the form of this, we bring the delta t over to the left side. That little algebra move arrived at what we now know as the momentum-impulse relationship. Because this quantity here, which is the force that's acting on it, and we'll assume for now that this is just a steady force, it's not changing in any way, although it can, and I'll show you how to deal with that. But if this is a steady force that acts for some amount of time without changing, then this quantity here on the left is what is known as the impulse acting upon the object. It's just like a force, except that we multiply it by however long that force is acting. And this quantity over here, the mass times the change in velocity, we call the change in momentum for the object that experienced that force. So momentum itself is just mass times velocity, but because we have a change here, this is a change in momentum. So this is a nice relationship, and I said we don't have to necessarily pass through the acceleration idea if we are asked about changes in velocity. And that's when I usually suggest that we use the momentum impulse idea. If we're asked for an acceleration, that would be fine. We may not need the time then, but usually you'll recognize if you're given a force and a time, they're almost always inviting you in that problem to try to solve it with the momentum impulse idea. So let's see a time where we might want to use this. So here's a typical example. 4-kilogram cart moving leftward at 2 meters per second. A force of 6 newtons acts on it for 3 seconds. How fast is the cart moving now? And I realize now that I wasn't real clear, so it's not ambiguous. We're going to call this a positive or a rightward 6 Newton force. One reason I put the leftward and rightward stuff in here is I want to reinforce the idea that forces, velocities, and momentum, those are all vector quantities, and you must pay attention to the direction part. Here we can indicate the direction by positives and negatives. Sometimes you have directions that aren't that simple to describe. For example, things going off at angles. When you start dealing with 2 dimensions, then we've got to be more specific and work through it with some more formal vector approach. But for now, we'll just imagine we're on a track, perhaps one of your lab tracks or something, and everything can move only left or right. So how would we apply this here? Well, let's look at what we have. This quantity here, of course, is the mass of our object, moving leftward at 2 meters per second. What that tells me is my initial velocity, I'll call it VI, is -2 meters per second. That negative, I will use the convention where leftward is negative. Here's our force, the positive 6 newtons, and it acts on it for a certain amount of time. That, of course, is our t. We would call that a delta t. A lot of times we just call it t for short. Every time, almost every time that we deal with in these problems is a time interval. It's amount of time, not a mark on a clock. So most delta t's are just abbreviated as t's because they're so common. And we want to know how fast the cart is moving now. So we're looking for the final velocity. So if we rewrite this statement, F delta t equals m delta v, all I'm going to do is rewrite delta t with really what we mean by a delta. That's the final minus the initial quantity. And that's true for velocities or any other quantity for that matter. So what are we looking for here? We're looking for the final velocity. So I would work through this in a series of algebra moves. I would probably first divide by the m, and then I would add bi. Now I did 2 algebra moves there at once. Hopefully you can handle that. If not, make sure you can go through and do those 2 steps yourself. I like to do my algebra symbolically before I plug numbers in. Now I'm going to go up to the description of the problem and plug my numbers in. So we have a 6 Newton force, and that's a positive, so I'll just leave the sign off of it. Multiplying it by the amount of time that lasts. So that quantity right there that I've just written, 6 times 3, that's 18 Newton seconds worth of impulse. Okay? Then when we divide it by the mass, our mass is 4 kilograms. And we're going to add it to, oops, I wrote the symbol there, our initial velocity, which is leftward at 2, so that's a negative 2 meters per second. All right. Now the units might seem a little unusual here. You say we got Newton seconds over kilograms. Well, remember that a Newton is a kilogram meter per second squared. So this all here in this first term is equivalent to a meters per second. So we can certainly subtract it or add it to another meters per second. So what do we have here? We got 18 on top divided by 4. That's 4.5, 4.5 meters per second. And we're going to subtract 2. It's equivalent to adding a negative 2, which means we have 2.5 meters per second as our final velocity. So can you picture this here? So we're moving leftward. Partly what that force did is it stopped the leftward motion, but then we still had a little more time with that force acting that it gave it some rightward motion. So all the while this 3 seconds was going on, we were changing the motion of the car. By the time that the 3 seconds was done, then we were up to 2.5 meters per second. So there's a kind of a typical example with a nice steady velocity. But I'm going to make a couple other short videos here that describe other ways we can describe impulse. And I'll just write them down here and then I'll leave it if you want to see the other video. Impulse can also be described as the area under the force versus t graph. And I'll use under in quotes because sometimes it's not really under when you draw it, it's over. So I'll have a separate video that describes how to find the impulse from the area under a force versus time graph. Area could also be equivalent to the integral of force with respect to time over some period of time, t initial to t final. Now, if you're just now in calculus, or maybe you haven't taken calculus yet, this is going to be a very new idea. So I'm going to have a different video that I'll go into a little bit more detail on what exactly that symbol means and how you calculate it. It's not hard to do, I promise. I can show you in that video, but I think I'll leave that to a different one. Perhaps if you've seen this before, you'll know just exactly what to do with that, and it wouldn't be necessary for you to watch anything more. So I think we'll stop that here. That's enough of an introduction to get you going, and you go through and see what more you need for your help. Good luck.